Hello. I am ready to get my butt absolutely handed to me on these. I don't know what it is about this lesson, but it's giving me extra troubles. The concept of a differential, the concept of a tangent plane should be fairly straightforward. Remember, the normal for this tangent is just A, B, C, because that gets dotted with x minus x naught, y minus y naught, z minus z naught, and because the normal and any 2 points on the plane would make a right angle when those vectors uh, intersect, their dot product, their cosine relationship would be a 0. So I dot these and I get down to a semi-standard equation of a plane. Now, let's break this down and get it to be kind of z-centric. Right through as we continue on, z is really going to become a function of x and y, meaning I give it some xy input and out comes a z output based on that xy combination. So here we go. Let's do this and get this to become z-centric. Divide, or let's move this c over. Divide both sides by negative c. But let's take a minute and break down what these things are before we write our final conclusion. Right, let's just for a moment, because we're in the partial derivatives unit, let's hold y constant, meaning this distance is 0, the b term gets canceled out, and it looks like this. Maybe even a little more familiar, something like this. Right, y minus y naught equals slope times x minus x naught. All of a sudden you realize this thing is just a ratio, where the a portion of the ratio belongs to x and the c portion belongs to z. You can kind of see this idea of slope forming, where this is a ratio of x to z that's then being multiplied on my change of x. And so that idea is going to kind of cascade down from there, giving me this formula. If I take this as a change of z related to x, we know that as a partial derivative times the change in x. And this one times the change in y. Now I will admit those negatives disappeared for the sake of sake. Again, if my derivative was negative, my calculation would take care of it. This isn't like a perfect analogy, but it's good enough to show you where this concept came from, where this idea comes from. Is this rise over run, but it's kind of... And remember with me, these are partial derivatives. Because z is dependent on x and y, both of these things are these partial derivatives at the coordinate. So like this is the partial of x and I plug in the coordinate, or the partial of y where I plug in the coordinate. Where both of these are the part of z that changes due to x and the part of z that changes due to y. Now that we've defined this, let's do a tangent plane equation, much simpler than the theory states, because it's just going to be partial times change plus partial times change, and you'll see that concept continue to show up throughout this lesson. Z minus 3. Oh wait, what am I doing? I'm getting ahead of myself. Let's do these partials real quick. Partial of x would be 4x, and I'm going to evaluate it at the coordinate, where when I plug in the coordinate 113, I would get 4. My partial at y would be 2y, where again, I'll plug in that coordinate 113, and I'll get back 2. And so that's this idea of saying, hey, when I have a partial, I have to evaluate it at the coordinate, in this case 1, 1. The 3 comes over here, and that's where it's taken care of. Now I'll do my f sub x times my change in x, my f sub y times my change in y. How great. So for every pace or portion I move on x, I would change at a rate of 4, whereas for every change on y, I would move at a rate of 2. And this only works in the neighborhood of z. Again, I could distribute and simplify this guy just a little bit, something that looks like this, to get it into a more normal format, but this is it. This is the plane that just kisses my elliptic paraboloid at the coordinate 1, 1, 3. So we call this an approximation. In this neighborhood, this tangent plane just barely rests on the surface and approximates in the local area. Well, let's just take it one tick further. Instead of 1, 1, 3, let's take it to 1.1, 1.1. So if I were to do the actual calculation somewhere out over here, where I'd have z equals 2 times 1.1 squared plus 1.1 squared. I would get 3.63. So that's where my actual elliptic paraboloid is. But let's now go find where would my approximate be and how close is that distance. For my approximate, it's typically easier to use this one. So I will. This thing is going to be my approximate. I just want to make sure I keep them labeled because there is a good difference. Four times 1.1 minus 1 plus 2 times 1.1 minus 1. And then also, I'm going to move over this 3 and add it on at the very end. But I want you to see, this is the change due to x times the change in x. The change due to y times the change in y. And then over here, I'll add the 3 at the very end, where I'd get 3.6. Very close, right? 1% difference. A very close. A pretty good approximation. Well, let's think about those approximate distances, right? Where my approximate distance would be 3.6 minus 3. I got 0.6 as the approximate change, where the actual change would be 3.63 minus 3, where I'd get 0.63. And so I would have this gap between the approximate tangent and the actual curve coming off of it. That would be my error, and I would call my error in this case 0.03. The difference between approximate and actual. Now in word problem concepts, I might turn this into a percentage, I might divide it out, but that's the idea here, that's my error. Now down here it asks for a linearization. That's what we did here. And I'll explain in the next box. I just want to get an example out of x comma y would start at 3, and then for every change in x, I would multiply it by 4. And for every change in y, I would multiply it by 1, because that's my rate of change I found up here. As z changes by 4, x changes by 1, rise over run. As z changes by 2, y changes by 1, rise over run. So that's the concept that's coming out of here, is that as my x and y change, they'll be multiplied by that scale, by that slope, and then I'll take 3, which is my base coordinate, and it'll be moving away from that 3. So this idea of point and change is really important in this world of differentials, tangent planes, and approximating error. So again, the idea here is that this is dz dx. They're partial z, partial x. This is partial z, partial y. And then I multiply it by some change in x. And I multiply it by some change in y. So then I have a value of x plus the change in z due to x, and the change in z, oops, tragic, the change in z due to y. And so there's nothing else that would affect change on z, because z is dependent on x and y. We define that at the top. So now I'll have my original point, and then I'll have my two directions of change added to that original point to approximate what's happening in that neighborhood around the coordinate 1, 1, 3. And that's the language I would like to use: nearby, neighborhood, something close by. So that is the linearization, and it'll approximate in an area around AB. Well, that area around AB has some amount of change, delta x and delta y, that moves me away from my original coordinate AB. I'm going to have AB plus some change, and the change is in those two directions. And the derivative, the slopes, are based on that original moment. And then it's multiplied, where that change gets eliminated and all that's left is dz, a change in z. This change gets multiplied and eliminated, so all that's left is a change in z, dz. And that gets output here. My original z, a little change, and a little change. But that little change has special names depending on its context. Are we talking about the actual change or the approximate change? Well, the difference is found in two ways. First is dz. dz is purely the change that's based on the approximate, where I'm going to take that partial change and multiply it by the change. That partial change and multiply it by the change, just like we did here. And I would end up with only the change in z. In this case, the linearization has that original point. dz is basically the linearization without that point. You can kind of see it happening here. Well, that's my approximate change, but my actual change is the beginning minus the end. That 1.1 minus 1, and seeing what the change in height is based on those two things. So if I went back and contextualized it in this example, the dz, the approximate, would be 0.6, because my tangent plane changed by 0.6 when moving from the tangent moment to above 1.1, whereas the actual change that the actual curve endured is 0.63. Now, that change can depend on concavity. One could be greater than the other. And honestly, as we get closer and closer and closer to that tangent point, the change is negligible. They're basically equal. And last but not least, error would be the difference between these two. And that error is due to the line curving, which is from second order or higher terms, the curvature of the thing. All right, so we know how to write a linearization: point plus change based on x plus change based on y. We know that that change can come in two different ways, whether it's an approximate change based on the tangent line, or the actual change, taking a later output minus the original output. Again, I really want to build up this concept of differentials in our mind. So if I'm looking at this thing again, my actual change would be this moment here. This coordinate would be f of a plus delta x and the output of it. I don't want to write it out that bad, but that would be the height at that moment. And I would find delta. Delta is this whole change from beginning to end. This whole thing would be called delta y. My bad. Stuck in the 3D mindset. But the approximation for that change would be this. And again, we see it. We know this. as dy dx. And in these cases, delta x is the same as dx. That's why dx makes nothing, because x is generally the only independent, so I'm less concerned about that. I multiply by that delta x or dx, and out comes dy. The change in y, the delta y, is the same as dy when the change in x is sufficiently small. So as we get closer and closer and closer, this distance gets smaller and smaller and smaller until we assume there's basically no distance. And if I'm labeling, oh, what a freaking crime against humanity. I can't believe I did it. This is delta y. Shame. The coordinate minus the coordinate is delta y, where the approximate minus the actual is dy. That's freaking tragic. I'm really frustrated I did that. Hopefully you can hear my frustration, why I'm trying to be really clear in this video, because my lesson today was convoluted in this concept. So I really am trying to clarify. The actual is the delta, the differential is the approximate. And again, my error lives right in here, the distance between the two. The same idea applies in 3D. The same idea applies in 3D, where I'm not going to make the mistake this time. Again, this is my original coordinate, and now this thing grows as it moves. The tangent plane is this flat surface, where the actual surface itself has this curvature to it. I see that my final output is up here. So this distance is my delta, 1000% sure. It's my delta z, my change in height from beginning to end. But I made this tangent plane, and this tangent plane approximates that same change. And the closer I get back to the original coordinate, damn dude, I can't believe I drew that too. It should be about here. But the idea is still going to hold true, folks. Don't kill me. This goes surface to surface. The approximate goes surface to tangent. Again, we see that same formula coming out. The partial due to x times the change in x plus the partial due to y times the change in y will only leave me with my changes in z's. And you can see it here in the formula, right? These will essentially eliminate, leaving me just the change that's due to the x and just the change that's due to the y. And since nothing else enacts change, I will have my total change. My delta end point minus the beginning point. And it goes beyond into further dimensions, where delta w would be the end point. Right, this original plus some change, and I subtract them, where that differential is going to have those canceling, approximating, slope-ish differential terms. I'll write a word problem or two to finish us out here. The base radius and height of a right circular cone are measured like this. Right, circular cone, my formula looks like this. 1/3 pi r squared h. And in this case, I've done the work for us. We get 2617.99 for our volume, centimeters cubed, of this beautiful right cone. Now, if I want to find the estimated error, the estimated approximate error, I'm going to take and go find dv. In the real world, we really only use dv because we're using the approximator for a reason. If I know delta v, why would I even bother with the approximation? If I know the actual, why use the approximation? So here we are using the approximation. This change in v is going to be partially due, dang it, to r, that should be a partial on the bottom, plus the part that's due to h. All right, and so I'll take my partial derivative of this function times dr. I'll do my partial times dh, and now I'll plug in all of the pieces. My r is 10, my h is 25, My dr, that's an error measurement. That's how much it slightly changes by 0.1. And the same with dh, 0.1. So I plug in all those values. I'll write out the big ugly phrase, 2/3 pi 10, 25, 0.1 plus 1/3 pi 10 squared, 0.1. And I get my final answer at 62.83 centimeters cubed. Again, what that means is absolute error. The absolute maximum error is 62.83. So that means the volume of this right circular cone could be anywhere in this region. The actual volume would be 2617.99 plus or minus 62.83. Right? That's our tolerance. That's our plus minus. That's our manufacturing error as we go through and make this right circular cone. Next up, we're making a rectangular box, and again, we know the volume is just length times width times height. So I know my dV now is in 3 variables. Be careful. The partial with respect to h is just LW times dV dH. Dang it. I knew I was going to make a mistake. LW times dH. Then I would have LH times dW. And last but not least, I would have WH times dL. You can see the 3 dimensions forming here, the 3 multiplications where a slight error in height times length and width, plus a slight error in width times length and height, plus a slight error in length times width and height. Give me volume, 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 and that'll make my total differential in volume. Again, I can plug in all these things. 75 times 60 times, in this case, my error is 0.2. I could have 75 times 40 times 0.2 and 60 times 40 times 0.2. And that'll get me my total dV. I trust you to get out the calculator on this one. All right. 1,980 centimeters cubed. That's a huge number. But what does that mean in the context? Like up here we had our absolute error. Let's try it as a percentage error. For that, I need the original volume. The original volume, 75 times 60 times 40, would give me 180,000. So then my percent error would come out there. Would be this 1980 out of 180,000. Where I find out that I get 1.1% error. So in context, the error is not as large as I was worried it was. Thank you for surviving and thriving here with tangent planes and linear approximations. Just remember that the differentials are the ones that cancel. The differentials are the approximation, where the deltas is the actual subtraction from beginning to end.